So in this recording, we're going to talk about solar power system design calculations. So this is our general view of our solar power system. So we have a couple different things that we need to define here. So how we have is everything connected, but first let's start with the load. So the load is something like a light bulb or a fridge or anything that uses electricity. So you can think about anything you plug in your house. In this case, it's going to be plugged into the solar power system to be powered. So right now we're going to be using, in this example, a 100 watt AC light bulb. And we're going to be using it for 2 hours a day all year long. Then we have an inverter. So what an inverter does is it takes DC electricity and converts it to AC electricity. And it loses some electricity along the way. So we're going to assume that our efficiency is 50%. So efficiency a lot of times is labeled with a Greek letter called eta, which is right here. So that's why we have that. So whenever you see eta, think efficiency. And our inverter has a maximum power rating of 450 watts. So we'll have to take that into account. Also, in our system, we have something called a charge controller. So what a charge controller does is make sure that the battery is not too overloaded or too drained, because batteries don't like to be overcharged or undercharged. So that's what the charge controller does. So it's really the decision maker of the solar power system. So this isn't exactly right, but we're going to use 100% efficiency for the charge controller. Normally it's around 80 to 90%, maybe a little higher. But just for simplicity's sake, we're going to use 100% efficiency. We're also going to say that the charge controller provides 10 amps maximum amperage. So that's its sort of upper limit rating, just like the inverter has an upper limit rating. We're also going to include some batteries in our system. Now, right now we don't know how many, so how we rate batteries is something called amp hours. So again, 1 amp hour is providing 1 amp for 1 hour. So we're going to say our battery capacity, each battery can hold 5 amp hours. So we'll have to figure out how many we need for that. Then we also have our solar photovoltaic modules, which take electricity from the sun, or take sunlight from the sun and make electricity. And we're going to say they're 20 watts each. So again, we're going to have to figure out how many of those we want. The other thing we have to note is that everything but the output of the inverter is 12 volts, and it's DC. So from the solar module to the charge controller is 12 volts, from the charge controller to the battery is 12 volts, and from the charge controller to the inverter is 12 volts. That's all DC. Then the inverter outputs 120 volts AC, just like what you use in your home. Okay, so that's the overview of the system. So how do we choose how many of these components we need? So we want to start with all the steps to solve for designing a solar power system. So we start with how many inverters we need. So that's step 1. Then we figure out how many charge controllers are needed for step 2. We calculate how much the load uses per day. So we can calculate in step 4 and 5 how many solar panels and batteries we'll need. Okay, so we're going to go through this step by step. The first step is we have to figure out the input power to the inverter when the load is on to decide how many inverters are needed. So let's start by finding out the input power of the inverter. So if we remember, the general efficiency equation is that the efficiency equals the output power over the input power. And so since we know from the previous slides, we know the output power of the inverter and we know the efficiency of the inverter, we solve for the unknown, which is input power. So input power equals output power divided by the efficiency of the inverter. Then we plug in what we knew from the first slide and we solve for input power, and the output power again was 100 watts and the efficiency was 50%, so we get an output of 200 watts. So we know that the maximum power rating of the inverter was 450 watts, and since the power that we're supplying to it is 200 watts, we only need 1 inverter. Now this would, if we got greater than 450 watts, we would need more than 1 inverter. Okay, so that's step 1. Now step 2, we want to figure out the amperage the charge controller provides to the inverter to decide how many charge controllers are needed. Okay, so we know the power coming out of the charge controller to the inverter is 200 watts. So we have to figure out what the current is, though, because the charge controller is rated with a current rating. So if we remember that power equals voltage times amperage, we can again rearrange the equation for the unknown. That amperage equals power over voltage. And the power is 200 watts, and the voltage is 12 volts. So the amperage is 16.67 amps, coming from the charge controller and going to the inverter. Since our rating is 10 amps, and we're drawing 16.67, we need 2 charge controllers, because then our rating will be 20 amps for those 2 charge controllers. Okay, so now, to start our calculations for our solar panels and batteries, we first need to calculate the energy the load consumes in kilowatt hours per day. So we know that the light bulb consumes 100 watts for 2 hours per day. That was given. And we need to convert that to kilowatt hours per day. So how we do that is we start with 100 watts. We first convert to kilowatts by knowing that 1 kilowatt is 1,000 watts. Remember, kilo means 1,000. We also know that it uses 2 hours per day. So when we do our unit analysis, we see that we get 0.2 kilowatt hours per day. So that means that the energy coming from the charge controller is, again, we use that same equation we used before, except now we know that we're going to use energies, output energy and input energy instead of powers for this. And we do the same equation because we can use efficiency with energy or power. And we find that we need 0.4 kilowatt hours per day from coming out of the charge controller. Okay, so let's review a little bit what we've done so far. We found that we need 1 inverter and 2 charge controllers. We also found that going to the load is 100 watts when it's on, and so that's the power when the load is on, and the energy needed is 0.2 kilowatt hours per day. So then we also found that when the light bulb's on, the inverter is drawing 200 watts from the charge controller, and the energy it uses coming from the charge controller is 0.4 kilowatt hours per day. So what that means is we need to supply either from the battery or from the solar module that 0.4 kilowatt hours per day. So that's what we're going to talk about next, is how we can do that. So step 4 is to calculate how many solar panels you'll need in a certain location. Okay? So sunlight varies over certain locations. So what you're going to need to do is figure out how sunny it is in your actual location. What's nice is that the National Renewable Energy Lab has a program called PV Watts, which is very easy to use and is a simulation to figure out how sunny your area is. I've also made another instructional video on how to use PV Watts. We're not going to go over that right now. What we're going to go over is how you use the results from PV Watts. So I ran PV Watts for Wilmington, Delaware. You can see the city and state here. And what we're going to look at is how that performed over a year. Okay? So what PV Watts gives us as a result here is this little thing. And what we really want to look at is the 2 first rows. So what we're going to do is look at each of the solar radiation outputs for each month of the year. Now, what we're worried about is when the solar output is very low, because that's when we want to design for. We want to design for the worst case, because when the solar output's low, that means we might not have enough power if we design for the better months. So we can see that December is the lowest number in solar radiation. So that's the worst month. So that's what we have to design for. So we see that that's 2.88 kilowatt hours per meter squared per day. So, but what we need to look at is how we can use that 2.88 kilowatt hours per meter squared per day. It turns out this unit is equivalent to something called sun hours. And you can also think of it as having the units of hours per day of full sunlight. So that would be like 2.88 hours per day of full sunlight. And since we know what the solar panel produces, which is 20 watts at full sunlight, you can use it to calculate the kilowatt hours per day that one solar panel produces, like so. So we know that 2.88 hours per day is what the solar panel produces, its full output. We know that 20 watts is produced by one solar panel, and again we use our unit conversion to convert from kilowatts to convert from watts to kilowatts, and we find that one solar panel produces 0.0576 kilowatt hours per day. So then we need to figure out how many solar panels we need to produce what we need. So we know we have to provide from the previous step 0.4 kilowatt hours per day. So to calculate how many solar panels we need, we do the following. We take in 0.4 kilowatt hours per day, because that's what we need, and we divide by 0.0576 kilowatt hours per day for one solar panel. And this gives us an answer of 6.94 solar panels. Now obviously we can't have 6.94 solar panels, so we round up that we need 7 solar panels. So step 5 is now we need to calculate how many batteries we'll need for the system to work without sunlight for a certain number of days. So just think about if you had a storm system come through and it wasn't very sunny days, you'd have to have some battery backup so you could supply the charge controller and the light bulb to turn on. So what we're going to do is we're going to say, okay, we're going to just say 3 days is needed where it's going to be really cloudy or really rainy and we have no sun and we need to power it with all batteries. And we know, again, that the load uses 0.4 kilowatt hours per day, and over 3 days this equals 1.2 kilowatt hours. So that's what we need to size our batteries for. We need our batteries to be able to supply 1.2 kilowatt hours. But the battery size is in amp hours. So the first thing we need to do is convert 1.2 kilowatt hours into amp hours. And how we do that is, we know that when we divide watts by volts, we get amps. So we have kilowatt hours, we divide by volts, and we get kilo amp hours. And then again we do our unit conversion with kilo, that we know 1,000 amp hours is in 1 kilo amp hour, so we need 100 amp hours. And since each battery is 5 amp hours, you need to have 20 batteries to get the 100 amp hour total. So that's how we figure out the number of batteries. Okay, so lastly, we just want to review that we're finished with our solar power calculation now. Now we started off, we know we needed one inverter, right? We needed 2 charge controllers, we needed 20 batteries, and we need 7 solar modules. The next step would be to see how expensive this system would be. And I'll leave that as an exercise for you. Thanks for watching.